Good day, students. Welcome to the AP Calculus AB 009 multiple choice review series. This is part one. We're going to be going over questions 1 to 10. For the complete playlist of all the review material, you can go to macrosurf.com and look for AP Calculus, and you have access to that. All right, let's take a look at problem number one. Question one, we are to find the indefinite integral of cosine 3x dx. So this assesses your knowledge of u-substitution and also the antiderivative of cosine. Okay, so I'm going to use u-substitution here. If you notice, if I differentiate the innermost function 3x, I'll get a multiple of the other function dx. So if u is equal to 3x, then du is going to be 3 dx. Alright, but we need the dx isolated here, so we'll simply divide both sides by 3. We have du over 3 is equal to dx. Okay, so if we make our substitution, the problem becomes that the integral of cosine 3x dx now becomes the integral of cosine. Instead of 3x, we'll have u, and instead of dx, we'll have du over 3. Alright, and we can factor out the 1/3 here using a constant multiple rule. 1/3 times the integral of cosine u du. Now, what's the antiderivative of cosine? Antiderivative of cosine is sine u plus c. Now, one common mistake most students make is they don't remember if it's plus or minus. So you ask yourself, when you differentiate sine, do you have a sign change? Remember, the derivative of sine is positive cosine. Hence, when you integrate cosine, there is no sign change. Alright, so that's why we have a positive here. And then we'll plug in the value of u back into our equation. So it becomes 1/3 sine of 3x plus c. And our answer for number one is option letter C. All right, let's take a look at problem number two. Problem two is assessing our understanding of finite limits. We have to find the limit as x approaches 0 of this entire expression. Now, one mistake some students might make is they might confuse this with infinite limits. If this were infinite limits, all you do is you focus on the leading terms. So in this case, you have, this is the leading term here, and this is a leading term on the bottom right here. And if you're taking the limit as x goes to infinity, some students might say, oh wait, I'll just basically divide these two and I'll get 1 over 2, and my answer is option letter B. That is incorrect. Okay, so when we're dealing with finite limits, we do not focus on leading coefficients. What we do is we substitute and evaluate the limit. If we have problems, we reduce and completely and then see if we can evaluate the limits by substitution. So if you look at this situation right here, if I plug in 0 in the denominators, you can clearly see I'll have a 0 in the denominator, which is problematic. So that discontinuity, is it removable or not? Or is it an infinite discontinuity? The only way we can figure it out is by reducing this rational expression right here. Okay, so let's go ahead and factor this out. If you factor out the numerator, so let's rewrite the problem. Limit as x approaches 0 of 2x to the 6th plus 6x to the 3rd over 4x to the 5th plus 3x to the 3rd. So take out the GCF on top. It's 2x to the 3rd times x to the 3rd plus 3. And then in the denominator, you take out the GCF. It's x to the 3rd times 4x squared plus 3. Okay, let's not forget the limit as x approaches 0. Alright, what you see happening here is that we can cancel out this, two common factors, and now we have this limit right here, limit as x approaches 0 of x to the third plus 3 divided by 4x squared plus 3. And you notice that that discontinuity is actually removable because if I plug in 0 into this function, I do not have an undefined output. So let's go ahead and evaluate this function at x equals 0. So we'll simply have, let's see, I have a 2 up here, so 2 times that. So if I plug in 0, I'll have 2, and then this entire term goes to 0, times 3 in the numerator, over, in the denominator this goes to 0, and you're left with 3. If you reduce this, your final answer is going to be 2. So the answer is option D. Alright, question 3 says for the function f is defined above for what value of k, if any is f continuous at x equals 2. So this is a test on continuity. In order for this function to be continuous, the left and right hand limits must be the same. So we just basically equate these two functions together and set them equal to the value when x is equal to 2. Alright, so let's go ahead and do that. Alright, so let's write down the steps first. So what you're going to do is set 1 and 2. So let's call this equation 1, function 1 and 2. So set 1 and 2 equal to each other. Okay, and then you're going to plug in x. So let's call this step A, B, plug in x, and then part C, solve for k. Solve for k. So this is the plan of attack. Okay, so first thing we're going to do is set these two functions equal to each other. So we have x squared minus 3x plus 9 equals to k plus 1. That's kx plus 1 equal to kx plus 1. Alright, so we want to make sure that the left and the right hand limits are both equal to the value of both functions at x equals 2. So to make that happen, we're going to plug in 2 into this function. So you have 2 squared minus 3 times 2 plus 9 equals k times 2 plus 1. Alright, if we simplify this, we're going to get 4 minus 6 plus 9, subtract 1 from both sides equals 2k. And then we have 2k equals 4 minus 6 is negative 2 plus 8. And then negative 2 plus 8 is 6, divide both sides by 2, k equals 3. Okay? So when k is equal to 3, the left and the right hand limits will be equal to the value of both functions at that value, which is 2 times 3, 6 plus 1, which is 7. Alright? So this guarantees that both functions have the same limit at x equals, as they approach x equals 2. Alright, let's take a look at question number 5. It says a function f given by f of x equals 2x to the third minus 3x squared minus 12x has a relative minimum at x equals. So we have to find the relative minimum here. So this is basically using the first derivative test. So let's write down some information, formulas that's going to guide us. So let's say f, the function f is differentiable. Okay, it's differentiable on some interval I. So what do we know? We know that we have a min. If f, the function f changes from decreasing to increasing, right? If it changes from decreasing to increasing, it looks something like that. So you're going to have a minimum there. So if f changes from decreasing to increasing, what does that tell us about the derivative? We know that if the derivative of f changes from positive to negative, let's try that again. If the derivative of a function changes from negative to positive, that means that the function changes from decreasing to increasing. And if it changes from decreasing to increasing, that means you have a minimum. Okay? And it can also go in that direction also. So basically, if a function has a minimum, the function itself changes from decreasing to increasing. and its derivative changes from negative to positive at that x value, at x. Okay? So that's what we're going to use to solve this problem. Now, we need to know where this function is decreasing and increasing. And the easiest way to determine that is by looking for when the derivative changes from negative to positive. So how do we find that? We have to look for the critical points first, right? So critical points are where the derivative is equal to 0 or does not exist. This is a polynomial function. Um, it's never undefined, no corners or cusps. Um, so, or even vertical tangent. So what we're going to do is just simply find where the derivative is equal to 0. All right, to find where f prime is equal to 0. Okay, so let's go ahead and do that. So the function f of x is equal to 2x to the third minus 3x squared minus 12x. So it's the derivative of that using the power rule, term by term differentiation, will give us 6x squared minus 6x minus 12. Okay, so we want to find where is equal to 0. So what we'll do is set the derivative to 0, set is equal to 0. You notice that 6 is a common factor, so we can reduce that. X squared minus x minus 2 equals 0. And then you can factor this using the x game. Find two numbers that multiply to yield negative 2, and that will give you negative 1. And let's see, negative 2 and 1 works nicely here, so we can factor this into x minus 2 and x plus 1. So you have your critical point, so the points where the derivative is equal to 0 at the values that satisfy this equation. Okay, so basically you have x minus 2 equals 0 and x plus 1 equals 0. And then when you solve this, you have x is equal to 2 or negative 1. So we have those two options here, 2 or negative 1. So which of these is actually the point where the function has a relative minimum? So what we're going to do is we're going to make a number line with the intervals. So we're going to mark negative 1 and 2. All right, so this is interval 1, interval 2, and interval 3. All right, so we're going to compute the sine of f prime down here, and then that tells us the behavior of f. Okay, so in interval 1, let's pick x equals negative 2. Interval 2, something easy. How about we use x equals 0? And then the last one, how about we use x equals 3? Okay, so we're going to evaluate the derivative. Remember, we're looking for the sine of f prime because that's what tells us the behavior of f. All right, so let's compute the sine of f prime. So for interval 1, we're going to look for f prime of negative 2, plugging a value in this interval into our derivative function. So this is a derivative right here in simplified form. Actually, this is a derivative right here. So let's plug it in there. We're going to have 6 times negative 2 squared minus 6 times negative 2 minus 12. Okay, so this becomes 24 plus 6 times 2 is 12 minus 12. And then, so what we care about is the sign. So here it's positive. Sign is positive, so we put a plus here. And this interval, sign of f prime is positive. All right, let's move to interval 2. Interval 2, we're going to evaluate the derivative at x equals 0, f prime of 0. Plug it into the derivative function. So we're going to have 6 times 0 squared, write that properly, minus 3 times 0. Minus 6 times 0. 6 times 0 minus 12. Okay, now if you simplify this, you clearly see that it's going to be negative. We just care about the sign, right? Because this is 0, 0, negative, so this is going to be negative. on that interval. And then lastly, for interval 3, we have, we're going to look for f prime of 3. So that's going to be 6 times 3 squared minus 6 times 3, and that's minus 12. Okay, so 3 squared is 9 times 6 is 54. 6 times 3 is 18. Minus 12. Minus 12 and 18, if you combine them together, you get 30, which is less than that, so this is positive. Okay, so we have positive here. Alright, so what does the signs of our derivatives tell us about the behavior of f on these 3 intervals? Let me draw the lines here so you can clearly see what's happening. So what does it tell us? Well, it tells us that it's increasing on this interval, increasing, and then decreasing. What's that? Increasing here, decreasing, and then increasing. So where do you have a min? You have a min, you're guaranteed to have a minimum at x equals 2. Alright, so we can clearly see that our answer is option letter C. Okay, now for those of us who do not like this chart, I personally do not care too much about this chart. There is a quicker way of doing this. This is by taking advantage of the information that the second derivative tells us. Okay, so method 2 involves just continuing from the fact that you have 2 critical points at 2 and -1. You want to skip this chart. What you're going to do is use the following idea, which is that if f double prime is negative, okay, well, that implies that f is concave up at that value, and it also implies that f has a minimum. Okay, I'm sorry, f double prime is positive. So if f double prime is positive, you have an upward facing concavity of the function, and then that means f has a min there. So what we're going to do is basically look for the second derivative of this function, and then we are going to see where it's concave up on these 2 values. Okay, how do you know if it's concave up? The second derivative has to be positive, alright? So we know that continuing from where we were here, f prime of x is equal to 6x squared minus 6x minus 12. This is a nice function because it has a second derivative, so if we differentiate it again, f double prime of x is equal to 12x minus 6. Okay, now I'm just simply going to evaluate the second derivative at these 2 critical points. Whichever gives me a negative output guarantees I have an upward facing concavity and consequently a minimum. Alright, so let's do f double prime at 2. Let's just be lazy here and do the answer. We have 12 times 2 minus 6. F double prime is positive here. That implies that f is concave up at x equals 2. And also implies that f has a mean at x equals 2. And that gives us the answer. So we don't have to do all of this, use this chart, okay, if you don't like it. And then let's test, these are our 2 tests. Let's also test the other one just to illustrate the correctness of this approach. F double prime of -1, plug in -1 into the second derivative. This is -12 minus 6 is -18, that's negative. That implies that the function is concave down, okay, at x equals -1, which implies that f has a what? Has a maximum. That's the extrema at x equals -1. Alright, so we can clearly see that our answer is option letter C. So if the second derivative exists, you can always skip this chart if you don't like it, and then use that approach, is much faster. Alright, let's take a look at problem 6. It says that the function f is given by this fractal expression right here, which of the following is the equation for the tangent line to the graph of f at the point where x equals 1. So to do this, we need to know the equation, the formula for the equation of a line, okay? So let's write down the point slope form of the equation of a line. So that's given by y1. Let's write this down. Y minus y1 equals mx minus x1. Okay, the advanced formula for this using calculus is basically f of x minus f of a is equal to f prime of a times x minus a. Alright, so, well, we can just call this, make this y so that's consistent. So a much more advanced variation. Let's leave it at f of x to be consistent. So this is the much advanced variation of the equation of a line. Okay, so if you remember this, that's perfectly fine. So what this tells us that we need three things. The things we need are y1, m, and x1. Okay, which is the same thing as f of a, f prime of a, and a. So in this situation, x1 is basically our a. X1 is 1. Okay, next thing we need to find is m. Remember, m is the derivative of x. Okay, so we need to find f prime of a, but in order to find f prime of a, we need to find what f prime of x is first. Okay, so let's go ahead and find that. So if f of x is equal to 2x minus 1 to the 5th times x plus 1, then what is f prime of x? I'm gonna find this derivative using the product rule. So you know that uv prime is equal to v u prime plus uv prime. Now I'm gonna do this problem. I'll make a mistake, and I want you to see if you can catch my error. Okay, so observe this and see if you can catch my mistake. So I'm gonna apply the product rule here. So this is my u, and this is my v. So we're gonna do v x plus 1 times u prime is the power of 5 times 2x minus 1 to the 4th plus u, which is 2x minus 1 to the 5th times v prime, which is just simply 1. Alright, so that's the derivative. Did you see my mistake? The answer is right here. The mistake is right here. When you're differentiating, this is a composite function. You have to use the chain rule. When you differentiate 2x minus 1, you get 2. So this must be times 2. So please pay close attention to coefficients that are not 1 when you're using finding the derivative, so you can make use of the chain rule to make sure you have an accurate computation of your derivative. Alright, so that's the derivative right here. Now, should we simplify? That'll be a total waste of time, because what we're looking for is a derivative at a specific value, namely x equals 1. So f prime of 1, we'll just simply plug in 1 into this entire expression. There's no need to simplify, okay? It's a total waste of time, so we don't have to do that. So put in 1 plus 1. Let's try that again. 1 plus 1 times 5 times 2 times 1 minus 1 to the 4th times 2. Plus 2 times 1 minus 1 to the 5th times 1. Okay? Alright, so this is 2 times 5. This is 2 minus 1, 1 to the 4th is just 1. So this entire expression is just 1 right here. 1 to the 4th is 1 times 2. And then plus 2 times 1 is 2 minus 1. 1 to the 5th is 1 plus 1, which equals 21. Alright? So now we have f prime of a, or f prime of 1. F prime of 1 is equal to 21. What's the last thing we need? We need x1, m, this is our slope, and we need y1, okay, or f of a. The y1 is equal to f of x1, right? So it's basically f of 1 So where are we plugging 1 into? You have to be really careful here. We're not plugging it into the derivative that gives us a slope. We're plugging it into the original function right here. Okay? So to get y1, it's going to be 2 times 1 minus 1 to the 5th times 1 plus 1. Okay? So if we simplify this, 2 times 1 is 2 minus 1, 1, 1. And then 1 plus 1 is, you have 2. So y1 is 2. Okay? So let's rewrite our original formula. It points to the form y minus y1 equals mx minus x1. Plug in the measures we have. Y minus y1. Y1 is, what is y1? Again, 2. Y minus 2 equals, the slope is 21 times x minus x1, which is 1. Okay? So we have to put this in standard in slope-intercept form. So we have y equals 21x minus, so you distribute 21 to here, you have negative 21. And we add this 2 to it, you have negative 19. Alright, so there goes your final answer. Option letter B is our correct result. Alright, let's take a look at question 7. We have to find the indefinite integral of e to the root x over root x dx. So you just have to remember that the derivative, let's write it here, d dx of the square root of x is equal to 1 over 2 root x. Okay? So having a derivative formulas memorized can really aid your computation of derivatives and also identifying situations where u-substitution is applicable. So it definitely is applicable here because the inner function of this composite function, e to the root x, its derivative is a multiple of the other function right there. Okay? So let me make it explicit. So integral of e to the root x times 1 over root x dx. So the derivative of this is a multiple of that, as illustrated here. Okay? So we're going to use u substitution here. Let's call u. U is root x. So du is going to be 1 over 2 root x. If you apply the power rule to x to the 1/2, you end up with this. We don't have time to waste, so let's just skip that. Multiply both sides by 2, so you're going to have 2 du is equal to 1 over root x dx. So our integral now becomes the integral of e to the u. This entire expression becomes 2 du. Okay? We'll factor out the 2, so we're going to have 2 times the integral of e to the u du. We know if you integrate e to the u, you just get into the u, so you have e to the u. Let's not forget a 2 plus c. And then u is root x, put that right back, and then you're going to have 2 e to the root x plus c as your final answer, and our answer is option letter A. Alright, so for number 8, it says the function f is continuous in the closed interval 0, 6 and has the values given in the table above. The trapezoidal approximation for the interval from 0 to 6 of the function, bounded with 3 subintervals of equal length, is 52. What is the value of k? Alright, so let's go ahead and write down what the formula for the trapezoidal approximation is. T sub n is equal to, you know the area of a trapezoid, right? 1/2 base times 1/2 times the height times the sum of the parallel sides. So we have 1/2. The height in this case is going to be the length of the intervals. They're all equal subintervals. So basically, you look at what's the distance from 0 to 2, 2 to 6, 6 to, 4 to 6 is all 2, right? So that's the length of the subinterval. All right, so let's complete our formula. So we're gonna have 1/2 the width of every rectangle, it's w. Every trapezoid, and then times, we're going to sum up the basis of your trapezoid. Okay, so for that we're going to have y1 plus 2y2 plus 2y3 plus plus y sub n. Okay, so you double all the heights in between because you're sharing two contiguous heights of two trapezoids that are next to each other. So all the heights in between, the interior heights are doubled, but the endpoint heights are just single because it's just only one trapezoid. Okay, so this is the formula, and then where the width is b minus a over the n number of subintervals you have, and this is basically an approximation um, of the area from a to b of some function. Okay, all right. So let's go ahead and apply that here. So we already determined that the width of our intervals is 2. If you wanted to work it out, w is equal to 6 minus 0 over 3 subintervals. 6 over 3 is 2. We already know that. So let's go ahead and work this out. We have the trapezoidal approximation is 52. Okay, as indicated here, equals 1/2 times the width is 2 times I'm gonna do it step by step here. I can skip steps, but I want to make sure everyone understands it, so I'm gonna do it the long way. So equals f of 0, okay, plus 2f of 1. I'm sorry, it's 2f of 2 plus 2f of 2 plus 2f of 4 plus f of 6. All right, so that's what I'm evaluating the function in this order. We can think about this as your x1, x2, x3, x4, and then f of x1, f of x2, f of x3, f of x4. All right, you double only the heights in the middle. Okay, so there goes the application of your trapezoidal approximation. So you have 52 equals, these two cancel out, and then we need to consult the chart. F of 0 is 4. Scroll down a little bit. F of 0 is 4 plus f of 2 is k, so it's 2 times k plus 2 times f of 4 is 8 plus f of 6, which is 12. All right. So now we just have this resulting algebraic equation. If we solve it for k, that should be our answer. All right. So we have 52 equals 4 plus 16 plus 12 is 32. 32 plus 2k. And then we have 2k is equal to negative 20. Divide both sides by 2. And then you have k is equal to 10. All right. So our answer is option letter D. All right, so let's take a look at question number 9. It says a particle moves along the x-axis so that at any time t greater than 0, its velocity is given by v of t equals 4 minus 6t squared. If the particle is at position x equals 7 at t equals 1, what is the position of the particle at t equals 2? So this is a differential equation. It's an initial value problem. So basically we have this equation right here, v of t is equal to 4 minus 6t squared. So how do you get the position x from the velocity? Position is the velocity is the if you differentiate position, you get velocity, right? So this equation is the same thing as saying dx dt is equal to 4 minus 6t squared. Okay, where x of 1 is equal to 7. Okay, so this is what we're going to solve. When we solve this differential equation, then the result, we can use it to evaluate the position at t equals 2. Okay, so we're going to solve this by separation of variables. Let's put a t here. Using separation of variables, multiply both sides by dt. So you have d of x of t, the derivative of the position, is equal to 4 minus 6t squared dt. So we just basically integrate both sides. Integrate. And then you have the position function x of t is equal to, using the power rule for integration, you do term by term integration. You have 4t minus 6t to the third over 3. Okay. This can be simplified in, okay, let's not forget the plus c, okay? So this is our position function. simplify it a little bit more. X of t is equal to 4t minus 2t to the third plus c. Okay, now we need to find out what c is so that we know what the particular solution of our differential equation is. So to do that, we're just going to plug in these two initial values. X of 1 is 7 equals 4 times 1 minus 2 times 1 plus c. If you simplify that, you get what do we get here? This is 4 minus 1, 4 minus 2 is 2, so 7 equals 2 plus c, which implies that c is equal to 5. All right, so our differential equation, the solution, particular solution to our differential equation is, let's see, x of t is equal to 4t minus 2t to the third plus 5. So what are we going to use this for? It helps us to compute the position at any particular time. So we're asked to determine the particle's position at t equals 2. So we just evaluate the function, position function at x equals 2. So we have 4 times 2 minus 2 times 2 to the third plus 5. Okay? Simplify this. 4 times 2 is 8. 2 to the third is 8 times 2. It's negative 16 plus 5. These two will add up to 13. Subtract it from 16. You get negative 3. Final answer is option letter C. All right, let's take a look at the last question, question 10. This is assessing our knowledge of asymptotes, discontinuities, and behavior, okay? And limits at it as a function approaches infinity. So let's see here. It says the function f is given by f of x equals x squared plus 12 over x squared plus b. The figure below shows a portion of the graph, this graph here. Which of the following statements could be the values of the constants a and b? All right, so let's start with the horizontal asymptotes first. So what do we know about horizontal asymptotes? Y is equal to, let's call K is a horizontal asymptote, if the limit as x approaches plus or minus infinity of the function is equal to the value k. Okay, so we're looking at limits as a function approaches infinity or negative infinity to determine the horizontal asymptote. In this case, you can see that our horizontal asymptote is the function f of x equals 3. That's our horizontal asymptote here. All right, so how do we find it? How do we find our horizontal asymptotes? We basically take the limit as the function approaches plus or minus infinity. Let's use infinity here. Okay, so using this formula, this is a horizontal asymptote if the limit as x approaches infinity of the function ax squared plus 12 over x squared plus b is equal to the horizontal asymptote, which is 3. All right, so let's solve this equation and it will tell us what a is. Okay. All right, so you might be concerned about b, but you're going to see that it's not a valid concern. So if you're looking at limit as x approaches infinity, what happens is that you only focus on the terms that grow the quickest. Okay. So in the numerator, this is the quickest growing term. In the denominator, that's the quickest growing term. Okay. You only do this for infinite limits. Don't do this for finite limits like we were doing in number 1. Okay, that's not accurate. So focus on those two. So this problem becomes a limit as x approaches infinity of ax squared over x squared equals 3. You're going to reduce this, cancel out the x squares. And then you have the limit as x approaches infinity of a equals 3. This term is independent of x, so you just end up with a equals 3. That's your value of a. Okay? So you can basically cross off ABC. It's either D or E. Now, all right, so shifting our attention to the vertical asymptote piece. This right here, this is our vertical asymptote at x equals 2. Okay, so let's indicate that. x equals 2 is our vertical asymptote. Vertical asymptote. In this case, we have an infinite discontinuity. All right. So how do we find our vertical asymptote? Let's write that down. Partition my workspace. There. Yeah. So you have your vertical asymptote. Um, so vertical asymptotes, the vertical asymptote if a rational expression p of x over q of x is reduced. So basically, there are no common factors, okay? Because if you have a common factor, that's not a vertical asymptote, all right? So this rational expression must be reduced completely first. So the vertical asymptote is given by the denominator equal to 0, okay? Solved for x. So if you solve the denominator of a reduced rational for the equation equal to 0, for a value equal to 0, those x values will be your vertical asymptotes, or the points of infinite discontinuity. All right, so let's look at this equation. We have ax squared plus 12 over x squared plus b. Now, we don't have to bother about reduction here because the numerator has no real factors, okay? The factor is you're going to have imaginary terms there. All right, so all we have to do is focus our attention on the denominator since the numerator is prime. We already even know what a is, right? We can even put it 3x squared plus 12 over x squared plus b. So the numerator is prime, cannot be reduced. So all we just have to do is focus our attention on the denominator. X squared plus b has to be equal to 0. Okay, so we want to find the value of b here. All right, so the value of our vertical asymptote is x equals 2. So we're going to plug that in here and solve for b, and that will basically tell us what the value of b is. So let's see, x is 2, so 2 squared plus b is equal to 0, and that follows that b is equal to -4, and then our correct answer is option letter D. All right, so that's that. So thanks so much for taking the time to watch this intensive review series. For other updates, please feel free to subscribe to our channel, and do post a comments to let us know what you think about this presentation. The whole collection of playlists can be found on marcusself.com/calculus. Thanks again for watching, and have a wonderful day.